Pen physics again. We continue where we left off. Last time we did relativistic velocity addition, and we did from May 10, time zone 1, one of the problems that had to do with velocity addition, two protons going head to head. So today I will do from May 9. This is one question from time zone 1, H3. It is relativistic kinematics, so it has to do with proper length, proper time, how you find the time and the distance in motion. So it says spacecraft leaves the Earth at a speed of 0.80 c, the speed of light, as measured by an observer on Earth. And again, I'm going to use my vintage pens. So I'm getting I'll get the Parker Duofold, two of them. One is the junior, one is the lady Duofold, and the Pelican 100. And with the inks that I showed you yesterday. Okay, so it heads towards and continues beyond the distant planet. So you have a spacecraft that starts from Earth with this speed, 0.8 c, and goes towards a planet. So the planet is 52 light years away as measured by an observer on Earth. So an observer on Earth measures this distance in light years, 52 light years. When the spacecraft leaves Earth, Amanda, one of the astronauts in the spacecraft, is 20 years old. The Lorentz gamma factor for the speed is 5/3, so we don't need to calculate this. But in general, you should be able to calculate this if you're given the speed. Now, the first question is calculate A1, calculate the time taken for the journey to the planet as measured by an observer on Earth. So that's important, who is observing this distance. So we can simply say that an observer on Earth sees this distance, 52 light years, and remember this light year is a distance covered by light in 1 year. So an observer on Earth measures this distance, 52 light years, and sees the speed of the spacecraft to be 0.8 c. So this is just a simple kinematics problem. So let me write down the question. This was from May 9. This was time zone 1, H3, and we're doing the question H3. So the first one is the time taken for the journey according to Earth. So the time is simply distance over speed. Okay, so according to the Earth observer, this distance is 52 light years, and the speed is 0.80 c. So now light years is basically the speed of light times a year. So you can see that this will cancel this speed, and you will get the result in years. So it's 52 divided by 0.80, and you do that and you get 65 years. So the Earth observer will measure 65 years until the spacecraft reaches the planet. The second one, calculate the distance between the Earth and the planet according to Amanda. Amanda is in the spacecraft. So what's the distance? Well, it's not 52 years. This would be the distance measured by the Earth observer. Now remember, Amanda is in the moving frame. So she is actually measuring the length contraction. Why is that? Because she's moving, and an observer that is moving and measures a length always measures a contracted length, not the proper length. So we can say, let me get my other Duofold pen, and again I can fill in some ink as I need to, because I don't actually fill the ink sacs with ink, so I need just to occasionally dip this into my ink bottles. Remember, this was the brown Carandas Grand Canyon, which has a very nice brown, and this was the blue. So B was actually, this was 1, this was 2. It's not B. B will come later. The distance between the Earth and the planet. So this is now length contraction. Okay. So L is equal to L0 divided by gamma. Length contraction. And L0 is remember, this is the proper length. Okay, so I do have, in this case, the proper length is the 52. Because the Earth observer measures stationary points, measures it's not moving. The Earth observer is not moving with respect to the things that they measure. So they do measure the proper length, which is 52 light years. So the moving observer will measure L as 52 light years over gamma, which is 5/3. And the answer would be, if you do this with a calculator, 31.2 light years, or approximately 31 light years. So that would be the answer to A2. A3 says, calculate Amanda's age as the spacecraft goes past the planet. According to Amanda, now when the journey starts, Amanda is already 20 years old. So whatever time we find for the observers in the spacecraft, we have to add 20 to that. So the question is, what is the time measured by the observers or Amanda in the spacecraft? Well, they do measure the proper time, because they measure this. Amanda is not moving, measures 2 events, beginning and end, according to her. So she's measuring the proper time. So we can say that for number 3, that Amanda measures proper time. So that would be T0, T over gamma. Now remember, gamma is always greater than 1, and the proper time is the least time measured by any observer. So it's T over gamma, and T, we found this to be 65 years. This was from question A1. And gamma is 5/3. So this comes out to 39 years. So finally, Amanda's age is equal to 20 plus 39 is equal to 59 years. So this is how old Amanda is, according to her, of course. Now, we come to B. As the spacecraft goes past the planet, Amanda sends a radio signal back to Earth. Calculate, as measured by the spacecraft observers, the time it takes for the signal to arrive at Earth. Okay, so this is for 3 marks, so this requires some thought. So what is happening? Let me get different piece of paper. Now I'll do it here. This, and I will use the Pelican for that. So as the spacecraft goes past the planet, Amanda sends a radio signal to Earth. So this is what is happening. This is the planet. And this is the radio signal sent back to Earth. And of course, this will travel with speed c, because it's an electromagnetic wave. Now, assume that this will take time t. Okay. during this time, the Earth being at a distance of 31.2 light years. This was the distance according to the spacecraft. So according to the spacecraft, the signal traveling with a speed c at time t will have to cover a distance c times t. And this distance must be equal to 31.2 light years plus, well, according to the spacecraft now, the Earth is moving backwards with a speed 0.80 c. So during this time, the radio signal has to cover this distance, this original distance, 31.2, plus however distance Earth has traveled backwards. Okay, so to this 31.2 light years, I have to add 0.80 ct. Okay, because this is the speed the Earth is receding from the spacecraft, 0.8 c. And for that time t, this will be the distance the Earth will move backwards. And then, once you do this, basically you're done. This was the tricky part of the question. So then you can solve for t. It's just a simple equation. So take this to the other side. So 0.2 times ct is equal to 31.2. And finally, the time is 31.2, 0.2. The c's will cancel because this was light years. So this is basically c times a year. So this c will cancel this c, and the answer will be then in years. One more calculation, 156 years. Done. Okay, good luck.